We're going to start talking about ideal gases in this part of thermodynamics. Our definition for an ideal gas. So in an ideal gas. Okay, the molecules are moving very fast. There is no attraction between the molecules. And we're going to say that the collisions are perfectly elastic. There is no loss in kinetic energy. They behave like billiard balls. Now, the relationships between pressure, temperature, and volume. Okay, we're going to say as pressure increases, the volume is going to decrease. That's assuming constant temperature. Because as I increase pressure, I'm squeezing on the gas, the volume is going to get smaller. And if I was to draw it, it would look like this. P versus V. They're inverses, as one goes up, the other one goes down, so it's going to look like that. Now, secondly, as temperature increases, let's say the volume is going to increase. That's assuming constant pressure. So as temperature goes up, volume is going to go up. They're directly related. It's going to look like that. And then lastly, as temperature goes up, okay, the molecules are going to move around faster. They're going to bounce off of each other harder and off the walls of the container harder. That's going to make the pressure go up. And that's assuming constant V. So we're going to have temperature versus pressure, and that's going to look like that. Now, one of those is Boyle's law and one is Charles' law. I don't know which is which, and you don't need to memorize that. You just kind of have to know what's going to happen. If you think of the molecules as little billiard balls bouncing off of each other, remember as temperature goes up, they're going to move faster. Say in this one right here, as they move faster, they will get farther and farther apart, so the volume's going to go up. Or, like I said with this one down here, okay, as temperature goes up, they're moving around faster. If the volume can't increase, they're going to hit the walls of their container harder, and that's going to make the pressure go up. We put it together in an ideal gas law, okay, and it is PV equals nRT. P is pressure in, the unit for pressure is pascals, and you can abbreviate that PA, one atmosphere. Because a lot of times I'll give you pressure in atmospheres equals 1 times 10 to the 5th pascals. V is volume in meters cubed. T is temp in Kelvin. To convert, we should remember that the Kelvin temperature is the Celsius temperature plus 273. And it has to be in Kelvin. Earlier when we were doing the delta T's, like Q is MC delta T, it didn't matter if it was Kelvin or Celsius. But when you see a T by itself, like in this equation, not a delta T, it has to be in Kelvin. N is the number of moles. And R is a constant. It's 8.31. Now, this you saw written if the number of moles is constant. which it almost always is, I can rewrite this as P1 V1 over T1 is P2 V2 over T2. Sometimes it's easier to use this version of it, and sometimes it's easier to use this one. Now, here's an example. A sample of oxygen contains 20 moles at a temperature of 20 degrees Celsius and a pressure of 1 atmosphere. What is the volume? So A, we are given that we have 20 moles, so N equals 20 moles. Temperature is 20 degrees Celsius. But we have to convert it. So we're going to add 273, that gives us 293 Kelvin. And the pressure is 1 atmosphere. Again, we have to convert that to pascals, so 1 times 10 to the 5th pascals. And then we want the volume. So we can go to our ideal gas law, PV equals nRT. I'm going to solve it for volume before I plug in. So V is nRT. In order to move the pressure over to the other side, I have to divide. Divided by P. So that's going to be 20 times R is that constant, 8.31. Our temperature is 293. And on the bottom we have the pressure, which is 1 times 10 to the 5th. And if we solve this, we'll get a volume of 0.49 meters cubed. For part B, we want to know if the temperature is raised to 80 and the pressure is raised to 2, what will be the new volume? There's a couple ways to do it, but I want to show you using it this way. P1 V1 over T1 is P2 V2 over T2. So that's going to give me, we'll put in our originals. For 1, it's going to be 1 times 10 to the 5th. V1 was 0.49. And T1 was 293 Kelvin. Equals, now, the pressure is raised to 2 atmospheres, so it's going to be 2 times 10 to the 5th. We're looking for the new volume, divided by the second temperature, 80 Celsius, so I'm going to, over here, do 80 plus 273, and that's going to give me 353. So 353. And then I would cross multiply and solve, and I'll get an answer of 0.30 for the new volume.